Hello, and this is the start of Chapter 9. We're going to be doing a lot of new formulas and a lot of new stuff for you that should be building on things you already know. The first thing that we're going to be doing is something called the distance formula, and it really is the distance between any 2 points. One common misconception that I start off with, and I kind of do sometimes, is to describe if I have a square and I know that this is 1 and this is 1, how far is it from here to here, from one point to the opposite point? Just pause and think about that for a second, and then if you resume, you'll realize that we can't just say that it's 1. We have to think about a diagonal distance as being longer. We have this thing called the Pythagorean theorem that ultimately will tell us that it's the square root of 2, which is about 1.4, but it definitely isn't 1. So if we come back to this stage here, when we're talking about the distance between 2 points, if I labeled this point x1, y1, and I labeled this point x2, y2, I have 2 arbitrary points that exist on the same line. Given that, what we can always do is triangulate, or basically create a right triangle. So we got a right triangle going here, we have a right triangle, and bam. Now I have a right triangle. I know that I can find the distance between any 2 points as long as I have a horizontal distance and a vertical distance. So if I were to label this point here, this point in blue, this would have the same x-coordinate as the second point, but it would have the same y-coordinate as the first point. Think about that for just a minute. This is x1 here on the x-axis, this is x2, this is y1, and this is y2. What that means is that my base of the triangle, the bottom of the triangle, is a distance. That's a horizontal distance, and that would be x2 minus x1. My vertical distance would be a y change, would be a y2 minus y1. So if we kind of do this whole deal now from a perspective of what's going on with the distance, we can create a distance here and say, now we got a right triangle. I have this distance, this, and this. And I sometimes abbreviate the y's and the x's, and I say that this is the change in x and this is the change in y. And when we build the Pythagorean theorem, we're going to say that d squared is equal to the change in x squared plus the change in y squared. That triangle is a delta, and it means change. It means subtraction. So distance equals the square root of the change in x squared plus the change in y squared. Or as it's more commonly written, distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And that is the distance formula. It comes from the Pythagorean theorem. And let's remind ourselves of the Pythagorean theorem. In a right triangle, a squared plus b squared equals c squared. Let's write it out a little bit more formally. In a right triangle, and anytime I ask you what the Pythagorean theorem is, I want you to start with, in a right triangle, the sum of the squares of the 2 legs, that means the 2 shorter sides, is equal to the square of the hypotenuse. And the hypotenuse is, of course, the longer side. The distance formula, it describes a positive distance, and it's always positive, a positive distance between 2 points that will denote x1, y1, and x2, y2. These are just 2 ordered pairs. And you get a distance. You get a single positive number. The distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. This is a formula that from now on you must memorize. I don't think it takes much to memorize it, because to be honest with you, I memorized this thing. I memorized the change in x squared plus the change in y squared square rooted, because that matches the Pythagorean theorem. Let's go on down now and talk about the distance between points. Here's some practice. If I say that the distance between these points is my change in x, I can do a change in x of 4 minus a negative 6 squared, plus my change in y is 4 minus a negative 2 squared, and then all square rooted. 4 minus a negative 6 squared is 4 plus 6 squared, which is 10 squared, plus, that'd be 6 squared. 10 squared plus 6 squared is 136. 136, if I look at the last two digits, I know I can take out a 4. That factors into a 4 and a 34. Let's write it like this. So I get 2 times the square root of 34. Number 2, if I have distances that are actually different points, like one of the coordinates is a binomial, what I can do is, well, wait a minute, we first of all have this radical 8, so let's rewrite this. I got radical 2 plus 1, comma, radical 2, and then I have radical 2 minus 1, comma, radical 8, which I can rewrite as 2 radical 2. Okay, change in x. My change in x, let's do the first minus the second. Radical 2 plus 1 minus, this would be radical 2 minus a negative 1. Remember, we have to distribute the negative, so I've got a minus 1 squared. If you flipped it around, it's kind of the same idea. We have to distribute a negative. Yeah, that should be a plus 1. Sorry, I was doing the first point minus the second, and let's do the second one. We go first point, radical 2 minus the second, 2 radical 2, squared, square root. My radical 2's drop out. 1 plus 1 is 2. 2 squared is 4. Plus, this would be negative root 2 squared, which is 2. And I get the square root of 6. So that's my distance for number 2. Number 3 is kind of the same idea, except we're just doing it a different way. Find the coordinate c such that the distance between the points is 5. So now instead of saying distance equals, I'm going to say 5 equals square root of c minus negative 4 squared plus 0 minus 1 squared. And I get 5 is equal to, c plus 4 squared plus, and this would be 1. Now if I square both sides, because I have a giant radical, and then subtract 1, I can get 24 is equal to c plus 4 squared. Take the plus or minus square root of both sides. I get plus or minus 2 radical 6 is equal to c plus 4. And then c is equal to negative 4 plus or minus 2 radical 6. Next, we have the midpoint. The midpoint of a line segment, if I kind of just drew an arbitrary line segment, it's the point that's exactly in the middle of the endpoints. This is an ordered pair. It's not a distance. So since it's an ordered pair, what I have to do is, well, let's look at this. Midpoint of a line segment, if I kind of triangulate that, I have this part here, which would be the x's, and this part here is the y's. What this means is that my x point, my x part of this, is the average of the two x's, and the y's is the average of the two y's. This is the best way to think about midpoint, because midpoint can be difficult. If you think about it, it's an ordered pair, it's not a distance. So let me erase this and just kind of put a thing down here. It's the average x, comma, the average y. Some people like a little refresher in how to find an average, so we can say x1 plus x2 over 2, comma, y1 plus y2 over 2. The midpoint of the segments, we have negative 14 plus 10. So I get, let's see, negative 14 plus 10 over 2. And then I have 5 plus 6 over 2. Negative 14 plus 10 over 2 is negative 2. 5 plus 10 over 2 is 11 over 2. So there's the midpoint of that one. 1/2 plus 3 divided by 2. And radical 27 I can rewrite as 3 radical 3 plus 5 radical 3 over 2. If I look at the first one, I can multiply the numerator and denominator by 2 and get 1 plus 6 over 4, comma, and then I have 8 radical 3 over 2 for the second one. And that's the same thing as 7 over 4, comma, 4 radical 3. Number 6, find the coordinates such that the midpoint of segment AB is negative 1, 7, and the coordinates of B is 2, 5. So what I have here is I have this unknown point A. If I draw it out to B, that has coordinates of 2, 5, and my midpoint is negative 1, 7. Now, I sort of like to think about this and triangulate it as well. If we sort of draw a little fake triangle, I'm actually going to move this up here, and say, well, our average x and our average y pops in the middle of the x's and the middle of the y's. And I know my x's are 2, negative 1. What does the other one have to be? In other words, we're kind of looking to see what makes negative 1 fall in the middle of 2 and something else. Now, I'm going to translate this into a little easier way that doesn't require a picture. I'm going to draw unknown point A, midpoint with negative 1, 7, and point B at 2, 5. I call this the listing method. I made this up a few years ago in order to make this a little bit easier. What does this x point have to be? Well, 2 minus 3 is 1, and 1 minus 3 is negative 4. That creates a sequence to negative 1, negative 4. And then if I look at 5 to 7, the next one after that would be 9, if I added 2. Negative 4, 9 is, in fact, point A. That's an acceptable way to show it for me. There's more algebraic methods that use the definition, but I think this way is a little bit easier. Okay, next problem, we have the vertices of a triangle. Determine whether it's isosceles and whether it's a right triangle. And if it's a right triangle, find its area. Well, if I have ordered pairs, we can kind of plot these out. And I would almost recommend doing this on graph paper because it might be a little bit more of a visual to see. So I'm going to turn on a grid. And let's pop over here to the right and get a visual going. Let's draw a grid. Oops. And if I do the point 4, negative 5, and negative 2, negative 8, and negative 8, negative 4, then I have a triangle. Okay, question is it an isosceles triangle? And if it is, okay, let's connect the different pieces of this. So I think from a visual you can see it's probably not an isosceles triangle, but let's go ahead and prove it. Oops, it's not liking me right now. You're probably fast forwarding to the point of where I actually have this triangle drawn. Okay, got it. 4, negative 5 was point A. This is point B at negative 2. Oops, right here. And this is point C. Well, if I'm actually going to find a distance, let's kind of go back here. I want to find all three distances. So let's do the distance between AB, which is the square root of 4 minus the negative 2 squared plus negative 5 minus the negative 8 squared. And that gives me the square root of 36 plus 9, which is the square root of 45, which simplifies to 3 radical 5. Then I go the distance of AB, or sorry, let's go distance of AC. So I can do the square root of 4 minus negative 8 squared plus negative 5 minus 4 squared, and I get 12 squared, or 144, plus 81, which is, let's see, 225, square root of 225. The square root of 225 is 15. Lastly, let's do the distance of BC. Big square root. I do negative 2 minus 8 squared plus negative 8 minus 4 squared. I get the square root of 100 plus 144, which is the square root of, oops, sorry, not square root of 100. I did this wrong. That should be a plus here. Glad I did this out. I'm looking off of it. This should be a 36. So I've got, let's see, 180. And the square root of 180 would be, 180 can factor into, let's see, we can go 36 and 5, so that'd be 6 radical 5. So none of the same distances are the same. It is not isosceles, and that was the first thing. Because isosceles means that two of the sides are the same distance. Part B is if we say, well, let's take the longest side. If we look at the longest side, I can actually compare it here, here, and here, and see that the square root of 225 is the longest side. So that would be the hypotenuse. And let's just see if I do the Pythagorean theorem on that, I would get 225 is equal to 45 plus 180, and that is true. So yes, it is a right triangle. Finally, for part C, find its area. So I can do 1/2, and base times height in a triangle is leg times leg. And if it's leg times leg, what that means is that we we want to do 6 radical 5 times 3 radical 5, because the hypotenuse is not one of the legs. And that gives us 9 times 5, or 45. We could just say units squared. Let's see, I didn't draw a very good figure. Yep, plotted one of the points wrong. Apologies. You guys probably all saw that and are laughing at me right now. But now I can kind of see that, yep, it is a right triangle. Boom. Wasn't isosceles. So maybe that was supposed to happen, so I didn't give it away right away. I know you're not buying it. Okay, collinear points are points that lie on the same line. This is another big deal. We talk about these points being collinear, and you sort of have to have this idea now to get to the next idea. So if I draw a line segment, and I have an arbitrary number of points on that line segment, so let's say that we have, it's not liking my line tools right now, so I'm going to have to get over that. Oh, we got one. Let's see. Collinear points, this is a little geometry too for you. If this is point A, this is point B somewhere in the middle, and this is point C, and A, B, and C are collinear, all on the same line segment. This also means that if we take the measure of AB plus the measure of BC, we get the measure of AC, which is another way of saying that B is in between A and C. Maybe not be the midpoint, but it is. So then we have this last idea here of a perpendicular bisector. I'm going to sketch this a little bit more casually. Let's draw a line segment AB. A perpendicular bisector is a line. It's a ridiculously long line because lines themselves go on and on forever. But it is a whole line. It's not a line segment. It cuts through AB at a right angle, and it passes through AB at its midpoint. It chops AB into congruent segments so that AM equals MB. And it's characterized by a number of different features. Let's start with this. If a perpendicular bisector of a line is perpendicular to the segment at its midpoint, and if a point lies on the perpendicular bisector, let's just put a point up here, then that point is, well, let's see what we're trying to say. What's true of this point kind of up here, or even a point down here? If I were to draw a triangle from that point to A and that point to B, if M is truly the midpoint, and I know this is off just a little bit, but if M is truly a midpoint, then that means that these are are the same length. They're exactly the same length. That point is equidistant. I can write that down. Equidistant from the endpoints of the segment. Now, geometry, people. I can erase that and kind of do a simple little proof here, where I say that I have a little piece of a triangle here. I have right angles here. And I have another piece of the triangle here. And if I label this point P, then I know that triangle PAM is congruent to triangle PMB, or PBM. And that's true by side angle side. Which then means, in geometry terms, that line segment AP has to be congruent to line segment AB by corresponding parts of congruent triangles are congruent. So however you see it, we kind of know that these and that distance is the same. Any of these are going to help us build the perpendicular bisector, and there are two ways to do this. So we're going to teach you both methods. Method 1, the perpendicular bisector, and the question says find the equation of the perpendicular bisector in standard form, that's important, for line segment AB whose endpoints are 3, 5, and 9, negative 3. Some people really kind of like sketching these. So we'll throw a sketch off to the side, A and B, and A is 3, 5, and B is 9, negative 3. And I have this midpoint here, but I don't really need that for this first method. What I need is this arbitrary point somewhere up here along the perpendicular bisector, this arbitrary point P. And what I'm going to do is I'm going to draw red lines that represent the distance from P to A and the distance from P to B, and I'm going to label point P as x1, y1. Pause this if this is going too fast. That's the advantage of this thing. Because I'm introducing x1, y1, let's do this. Let's say let x1, y1 be a point on, the perpendicular bisector. So if that's true, then the distance between x1 and y1, the distance between x1, y1 and 3, 5 is equal to the distance between x1, y1 and 9, negative 3. Let's do two distance formulas. x1 minus 3 plus y1 minus 5, both of them squared, and both of them square rooted. All of it square rooted, equals, let's do the other one, x1 minus 9 squared plus y1 minus negative 3 squared, square rooted. This may seem like a lot. It's 4 foils. We can also square both sides and drop the radicals. So what we're going to do is, let's FOIL, like lots. x1 squared, I didn't really need to call it x1, y1. Let's just call it x and y. That's my bad. X squared minus 6x plus 9 plus y squared minus 10y plus 25 equals x squared minus 18x plus 81 plus y squared plus 6x plus 9. Look across the aisle. We can drop our x squareds. We can drop our y squareds. Simplify the left, and I get negative 6x minus 10y is equal to, plus 34 equals negative 8x plus 6y plus 90. And move everything over to the left side, and I get 12x minus 16y. Move the constant over to the right, equals 56. And simplify, divide by 4, I get 3x minus 4y is equal to 14. That is the equation of the perpendicular bisector by method 1. A little bit harder to think about, a little bit easier math. Okay, that thing is sticking around. Let's see if I can get rid of that. My computer's tired, it's been on all day. And I have about 17 minutes till a counselor meeting, so we got to get method 2 done. Method 2 is my preferred method. It is the method that I do. It involves 3 steps. Step 1, we are going to look at those 2 points and we're going to find their midpoint. So step 1 involves finding the midpoint of 3, 5 and 9, negative 3. You're going to watch how I find a midpoint quickly. I look at this and I say, alright, midpoints between those two. Average of 3 and 9 is 6. Average of 5 and negative 3. 5 plus negative 3 is positive 2. That'd be 1. 6, 1 is the midpoint. I circle it as a little check. Step 2. We find a slope. We're going to find the slope of the line segment. So the slope of AB is going to be equal to 5 minus negative 3 over 3 minus 9. And I get 8 over negative 12, or negative 2 over 3. Kidding. Okay, that's my second mistake of the day. If I make 3 big ones, you can kill me. Negative 4/3. Sorry, 3 minus 9 is negative 6. Okay, that's the slope of the line segment AB, so the slope of the perpendicular line would be a perpendicular slope of negative 4/3, which is positive 3/4, and I'm going to circle that. Step 3 involves point-slope form. We have a point, we have a slope. Let's go y minus 1 equals slope times x minus 6. Well, if I'm trying to go for standard form, let's multiply both sides by a 4. 4y minus 4 is equal to 3, distribute x minus 18. If I move everything over to the right side for x and y, I would get 3x minus 4y equals 14, which is the same thing that we had before. So that's a good check if you have the time. Okay, last problem. Find the points on the coordinate axis that are equidistant from points 5, negative 2, and negative 3, 8. So if we're finding points that are equidistant from 2 points, that's again the same thing as a perpendicular bisector between them. Pick your favorite method, but given the language of this problem, I'm going to say let x, y be points on, or actually we should just say points equidistant from A and B. Then I'm going to say x minus 5 squared plus y minus negative 3 squared equals x minus, oops, that wouldn't be y minus negative 3 squared, that'd be y minus negative 2 squared. Okay, there's 3, but I'm catching them, so then we go x minus a negative 3 squared plus y minus 8 squared. Now where's the big square roots? Well, the next step is to square both sides. So where did this come from? This is the distance to A on the left, this is the distance to B on the right. Let's double check since I seem to be making lots of mistakes. Okay, let's square the whole thing. X squared minus 10x plus 25 plus y squared plus 4y plus 4 equals x squared plus 6x plus 9 plus y squared minus 16y plus 64. So the x's are going to drop out, the y squareds are going to drop out. Let's do some moving of the x's to the left. I get negative 16x. Let's move the y's to the left. Plus 16, I get plus 20y equals, right side I have 73 minus, and I'm moving 29 over. Let's multiply through by a negative. I get 16x minus 20y equals 73 minus 29 is, let's see, that'd be 44. It'd be negative 44 since I multiplied by a negative. Then divide through by 4, and I get 4x minus 5y is equal to negative 11. And we're done. Homework's at the bottom. I can move it there, but you see it.